Good evening and welcome to this latest series of asset lecture. And we are very lucky to have distinguished Professor Ramaprakash here to give a talk on solar ultraviolet imaging telescope on board Aditya-L1 mission. Before we proceed further to the lecture, I request Professor Roja to give a formal introduction to the speaker.
Good evening. So it's my great pleasure to introduce today's speaker, Professor A.N. Ramaprakash from IUCAA Pune. So we fondly call him Ram. So Ram did his BTech from in 1992 from College of Engineering in Electronics and Communication from Thiruvananthapuram. And then he obtained his PhD in 1998 from working on astronomical instrumentation from University of Pune while he was working in IUCAA Pune. And then from late 97, I think early 2000, he was a visiting fellow in Caltech and then of course postdoc in Institute of Astronomy, Cambridge in UK. And then he joined IUCAA as a faculty in 2000. And his interests are primarily on astronomical instrumentation, but he also did work on dust polarization and ISM. And main interest, of course, Ram was on developing new technologies and instrument for ground and space-based astronomy. And some of state-of-art instrument which you have made for, I think, many different telescope was 1.3 meter Greece telescope, particular RoboPole, which is very popular instrument. I think adaptive optics also, I think collaboration between Caltech and IUCAA had made this thing for Greece and I think Kitt-Peak 2.1 meter telescope. And most recently, the instrument which is quite popular is WALOP, I think wide field infrared or linear optical polarimeter. I think both north and south hemisphere, which is a thing. Of course, late, I think he was the instrument PI of SUIT, Solar Ultraviolet Imaging Telescope on board Aditya-L1, which was launched last year, 2nd September. And also he's playing a key role as an associate program director of TMT project where India is participating. So today I think we're going to talk about SUIT. So I invite you.
Good afternoon, everyone. It's a pleasure back to be here at TFR. I think the last visit was pre-COVID. So COVID is our reference point for almost everything. So the last visit was pre-COVID for a workshop here with, I think, Manoj was organizing. Anyway, it's good to be here. I was not sure whether I'll make it today here because of the rains and the expressway closure and so on, but I'm here now and had a very good conversation with almost the entire astronomy department this morning. And unfortunately, I have to travel back today, but of course, I'm not far away. I'm in Pune. So we will be, we'll have a lot of opportunities to discuss. So today my topic is solar ultraviolet imaging telescope on board Aditya-L1. The instrument PI, that is why there is an I behind the PI there. It's very slow. I don't know. I use this pointer because the Zoom people can see it, but let's see if it works or not. And Durgesh is the PI, the real person who is using the instrument, and we can the main driver. And Srijit at Manipal is the project scientist. Of course, we have a lot of collaborators, co-investigators, and you can see a big banner of institutions who are involved in the program. Let me put this whole instrument in a little bit of context, why we are building it, what are the key science drivers which define the instrument's capabilities, etc. Of course, almost everything in astronomy in a quantitative fashion starts with Galileo, who was in this case also observed the sunspots and made notes of it. You can see sketches. And he also noticed that things move. Sun is rotating and the spots move around, and made a lot of, at that time, advanced information about the nature of these spots. But if you look at the same thing today, a sunspot would look like this with a modern telescope. So they are huge. The whole Earth could fit within typical sunspot sizes. They are enormous in size very often. And a movie of a sunspot shows that it's not a static system. It's very dynamic. You can see this umbra, the penumbra, and all these granule structures, which are continuously changing, all the convection cells moving up and down. So it's a very dynamic kind of object on the sun's surface. But that's at the large scale. And if you go to very small scales, we are talking about things which are at the level of few arc seconds across or sub-arc second even. You see these granules, which are also features in the sun because of the convection process, stuff coming to the surface and sinking and moving around. So you have structures on the sun at all scales, like arc second scale all the way to sizes which are very big, as in the case of sunspots and active regions. We also have transient phenomena like this, which are flares. You can see these arc-like structures, which are material flowing around the plasma tubes. And when the most popular theory, magnetic reconnection happens, the flux lines, material gets dropped along these tubes onto the photosphere, and photosphere gets heated, and you see these arc-like structures where the material hits the photosphere and heats up. So up here, when the reconnection happens, you get to see stuff in X-rays, but later when the material hits the photosphere and heats up, you get emission UV. And I'm saying this because this is one of the key drivers of SOOT. That's something which we want to see. For example, when we can get advanced warning from the X-ray and see when the next activity is going to come up in UV, and then SOOT can pick it up and observe at the very early stages of the flare initiation. And that's one of the science drivers for SOOT. Of course, at the other end, you have these huge ejections, material ejections, which is happening from the sun. And some of these materials are so large that you can, again, the amount of material you can see in this inlet and the Earth-sized object out there. There's this enormous flow of materials coming out from the sun. So what I'm trying to point out is all kinds of time scales involved and all kinds of size scales involved. And the sun is a very dynamic thing. And since it's the closest star, it's a good laboratory to study all of these activities. And then on top of it, there is, the natural eclipse situations. You get to see the corona of the sun. So on Aditya mission, there is a coronagraph also to study the corona, called VLC. SOOT would study the disk and coronagraph would study the corona. And from the corona, there is always, mass coming out of the sun, but there is also this interesting observation that if you look at the emission in the corona, emission coming from the corona, you see these lines which are of, high ionized states of iron, calcium, etc., which means this corona is at a very high temperature, like 1,000,000 Kelvin. This has been an enigma for solar astronomers. It's not it's still unsolved mystery. The question is not why the temperature is high out there. I mean, that is possible. Not difficult to have a low density, high temperature gas stuck against a high density, low temperature gas. We see that all the time in astronomy. But the interesting thing is, how does the energy which is required to heat it up that temperature goes through the intervening medium without getting deposited there and get there? What are the mechanisms to do that? That's what has been interesting. And that's a question which one would like to address, and SUIT would be a tool which will allow you to do that. I'll tell you a little bit later how that happens. But also in this movie, which is played out where I was already speaking, let me see if I can make it play again. Anyway, so the corona also has ejections. So there's a constant solar wind, and occasionally there are solar storms. So the corona ejects material in a storm, and these highly charged particles come towards Earth. If they happen to do that, they can create havoc in the environment around Earth in terms of our communication systems, power systems, etc., etc. So it's interesting for us to see, and even if possible, predict when such events can happen, or which of the active regions on the sun could lead to that kind of activity. And that would be an interesting thing to interesting capability to develop. I talked about these variations in the sun on timescales, which are seconds, days, minutes, etc. Sun also has variability at scales which are years. We all know that. So if I look at the sunspot pattern on the sun surface, this pointer is very slow. Sunspot pattern on the sun surface as a grid, and plot that over a long period of time, you get these beautiful butterfly diagrams where this is measuring the sunspot covered area as a function of latitude versus time. And you can see that, there's a nice pattern, 11-year cycle, the well-known 11-year cycle of sun. And they are all cycles are not same. Some cycles are much larger than the other cycles in here. And the fact that they are confined to these latitudes, plus minus 30-degree latitudes, that's also clearly obvious from that chart. So this is something which is interesting to understand. Why are these active regions behaving the way they behave on a very long time scale, like 11 years and so on, and what leads to that? And there's just another graphical illustration of the same thing. The activity on the sun, which is something like this at the moment. Sun is at the peak of the solar cycle at the moment. And now we'll start slowing down potentially by 2025. And at the quiet phase, it's almost nothing on there. And then it'll cycle back to the active phase again. So this is a long time cycle, all the way from seconds kind of time scale to years kind of time scale. And all this, if I look at the layers of solar atmosphere, all the way from the photosphere up there, you can see the temperature changes from about 1000 Kelvin all the way to up to 1,000,000 Kelvin in the corona. And the density changes 10 to the minus 11 to 10 to the minus 3 up there. And you see these patterns are all threaded. At the very bottom is the magnetic fields. And that each of these pick up a different height in the solar atmosphere. And you can see they are all threaded together. So they are not independent structures. And so what we really would like to understand is the dynamics of how these different features evolve through the solar atmosphere, what drives them, what leads to the energy deposition in the corona, etc., etc. So these are all linked. So it is important not only to study the sun, just one second, in this time scale, it's also important to study in a 3D fashion where you probe all the layers as simultaneously as possible so that you can study the evolution. Magnetic fields. Sorry? On the photosphere, yeah, magnetic fields. So the white ones are one of the polarities and dark spots are the other polarity. then you can see the structures through the atmosphere. As you go up the different layers, they match up. Each of these, because the solar atmosphere is optically thin, depending on the density and the temperature, by different wavelengths, you can pick different heights, basically. So that is a good tool to probe different heights in the solar. So each of these different colors is a different wavelength, picks up different heights in the solar atmosphere. So what is needed to study the sun is a variety of activities and phenomena occurring on the sun's photosphere and chromosphere, understand the energy transport mechanisms and quantify their effects on space weather, because all these particles shoot and come towards us. We need to understand this, and then the environment around us, protect our assets, for example, and monitor long-term variability of the sun in the UV. It's not just days, but over years, and quantify their effect in the sun climate relation. I'll come to that in a bit. When you all know UV is very important. UV is the radiation from the sun which directly couples to the solar atmosphere, absorbed by the solar atmosphere. So any variation in UV is important for climate studies. And paramount importance is to continuously do this over a long period of time. It's not enough to do this sporadically, but sufficient angular resolution, sufficient photometric accuracy over a long period of time over the full disk of the sun. That's a demand scientifically which is put on suit. So in order to do that, we have to put suit on a point in space where you can monitor the sun continuously, because that point is the Sun-Earth Lagrangian point. Sun is out there, Earth is out there, and about 1.5 million kilometers towards the sun is that first Lagrangian point. So that's where the satellite is launched into a halo orbit around that point out there. So of course, not to scale. So the satellite is orbiting in a very large orbit around that point, around L1. What we are trying to do, as I was trying to justify in the previous slides, is to study that part of the solar atmosphere. You can see height on this axis and temperature on this axis, also marked as what that layer corresponds to in the solar atmosphere. So that section where it is on the photosphere and the chromosphere and the transition from about few thousand Kelvin temperature to about 1 million Kelvin temperature. Probe all those layers of the sun with different wavelength probes and try to build a 3D tomographic map of the sun's features as they evolve. That's what we are trying to do. If I look at that in the solar spectrum on this chart, what we are looking at is this part of the spectrum. Okay, it's not the entire spectrum, but that's just a part we are trying to study in the solar spectrum. I'll come to in a minute why that is important. The reason is, if you look at the solar spectrum, looks by and large like a black body, especially at this visible and longer wavelength. The deviation from the black body is most prominent at that wavelength, in the UV wavelength. And the sun, by and large, is a very steady star. Its total throughput does not vary very much, in spite of all that magic going on at all time scales and physical angular scales. Very little total light variation happens, less than 1%, let's say. Out of that total variation, almost 80% of it is happening there. So it's the UV which is varying on the sun out of the total throughput, total output. So that's the part which is interesting to study. And although we know that as if we look at sun as a star, as a point source and try to study the total light, is the UV which is varying. Surprisingly, nobody has managed to study the sun's whole disk in this fashion over a period of time and understand what physical processes are leading to these changes in the UV. There are guesses, there are probably models, but there are not very little observational data of what activities on the sun is leading to this change in the UV wavelength. And that's what is crucial to understand. And that's what we are trying to do with SUIT. Focus on that region where the variability is the maximum and try to figure out by resolved imaging of the sun and multiple filters, build up through all the atmosphere layers, what must be happening to make UV vary the way it varies. Okay, that's what we're trying to do. Of course, in order to do that, you cannot sit on the ground and do. The UV is severely absorbed in the ground. That's the black curve is the best fitted black body curve to the real solar spectrum, which is in yellow. But what we'll see in ground is the red part. So you can't see much of UV sitting here. So you have to go to space to do that, especially to 200 to 400 nanometer. The way to study that is going to above the atmosphere. So that kind of fits the boundary conditions for an instrument to study sun in this context. And so I will list out here what the parameters are then. For SUIT, it has to have a spectral coverage of 200 to 400 nanometer with a carefully selected set of filters. The narrowband filters are selected in such a way that it picks up different layers of the solar atmosphere. And the broadband filters are selected in a way that you can study the UV variation as a bulk, and see how that couples to the solar Earth's atmosphere and what impact it has in sun climate relations. And we need a sufficiently large field of view to cover the entire solar disk as well as the area around it, part of the corona, which we can see, so that we can study the off-limb features of these ejections and coronal mass ejections, eruptions from the sun, and so on and so forth. We need a good angular resolution. I'll skip why the focal length, but this is directly coming from the angular resolution requirement, and aperture, which also defines what fine features you can see. Aperture is not defined by the signal, by the way, which is true for nighttime astronomy. Here it's defined by what resolution you want to get and what kind of photometric accuracy you want to achieve to study these features. Sun has a lot of structure on its surface, so there's a bright feature here and a dark feature. What kind of contrast should be delivered by the instrument so that the bright feature only contaminates the dark feature to a level which is acceptable to that 50 to 100 signal to noise ratio you want to achieve, and so on and so forth. So the scattering, so you're looking at a very bright source, so the scattering has to be controlled to very low levels so that your photometry becomes accurate enough. So that puts the overall requirement on SUIT. The instrument itself, onboard Aditya, is sitting on the side here on the top deck. This is VLC, the coronagraph, which was built by Indian Institute of Astrophysics. This is SUIT, and there is a host of other instruments. I will some X-ray instruments built by other institutions, Helios for high energy X-ray, and Solex for low energy X-ray. And then there are other instruments which will measure in situ the particle behavior, magnetic field, etc., at the L1 region. So in addition to remote observing the sun, also the local environment in L1 is measured by these other instruments. So it's a comprehensive solar observatory. So what is SUIT all about? I mentioned this, and this is just a credit slide. You can see a lot of institutions involved on the left side who are directly involved in the hardware activity. And of course, a lot of us, departments of ISRO was directly involved. I'll skip through this, people who are responsible for different parts. Anyway, these are the instruments on SUIT, the coronagraph, the soft X-ray and hard X-ray remote sensing instrument, and the in situ measurement instrument, particles and magnetometer. I'll be, of course, talking a little bit more about solar, which is what we are, SUIT, which we are responsible for. SUIT, and the real payload is sitting here, up there, on the side of the coronagraph. That's what it really looks like if you remove the multi-layer insulation sitting in the lab. At the top of it is a radiator, which looks at the 4K sky. and it's directly coupled to the detector so that the detector is cooled to sufficiently low temperatures. And if I look at a 3D diagram, light comes in, is flipped with respect to the previous photo I showed, unfortunately. Light comes in from there, from the front end. It's here. There's a door there. Light goes in there. There's a primary mirror, then reflects the light, goes to this yellow thing, which is the secondary mirror, comes here as a shutter, filter wheel arrangement, and then there's a detector assembly. So that's the entire optical train of suit. Relatively simple optical arrangement. But the key thing is it has these carefully chosen filters. It can take fast images nearly simultaneously and continue to do that almost autonomously. The science drivers, as I mentioned here, crystallizing them are studying this coupling and dynamics of the solar atmosphere, solar flare studies, especially the flare initiation process. What leads to the initiation of the flares in the beginning and what leads to the UV emission. Then the coronal mass ejection and space weather and sun climate studies. So those are the 5 dominant science drivers for SOOT. The filters appropriately has been chosen. You can see here, this probes the photosphere, this probes the sunspots, lower photosphere. In between, you probe various levels of chromosphere and the transition region. And these 3 filters are continuum filters, which will probe sun climate, space weather. They are broadband filters. Now, I mentioned about this issue with the solar coronal heating. Corona emits in extreme UV and X-rays. You can see this corona seen here. The ejections from corona, as it couples to the solar atmosphere, or even the UV variation, the radiation variation, as it couples to the solar atmosphere, you can see in this graph, for example, this is height in the solar atmosphere as a function of temperature. So when the solar minimum happens, when the activity of the sun is small, as the temperature as a function of height looks like this yellow graph, where when the solar activity peaks, which is around now, the temperature as a function of height. So it's a substantial variation in the temperature of the atmosphere as a function of height, depending on the solar state, which means it has a tremendous impact in what is going on in our atmosphere. This is all because of the UV variation. And if we can understand what leads to the UV variation, and we can understand, if we can a bit predict what kind of solar activity will lead to the space weather effective activities or sun climate effective activities, that would be a big thing. So that's what we are trying to achieve in the long term. And here is, of course, a graph which shows the density of different materials as a function of solar, as a function of height and different solar conditions. And so, of course, as temperature changes, density also changes. And this is just, I've skipped this graph because of time, but this just shows that these kind of enormous ejections have tremendous impact on our lives on Earth. Now, what is the challenge in building something like SOOT? We lay down why do we want to build SOOT? We lay down what the specifications are, but now what are the challenges? The most important challenge which we faced was the HR challenge. HR is human resource, more than anything else. The reason is, typically it takes several years, maybe decades, to train people for space instrumentation. But our space programs are far and so separated. So by the time we train a set of people, get them up to the speed, make payloads, launch them, then you wait till they disperse, evaporate off from the system. Then you start everything from scratch again. So this was a problem even for this. So it's difficult to retain HR across gaps between major missions. And that's a big problem. So suit had to be built almost entirely by freshers. And I'll show a slide next. You can see these are all kind of, BTech MSc students, which are kind of straight out of their graduation and so on. They had to be trained and built, made ready to. And this bunch of people, they are youngsters and they are all already lost to the system. It's such a pity. The next mission we want to start, we have to start afresh again, all the way from start. This such a, we need to fix that system. I'm not saying, I'm just making this statement here, but it's something for us to pay attention to and solve. Otherwise, these missions are going to take enormously long and unnecessarily the process of reinventing the wheel will happen. So that is one part, that's one challenge. But on the technical side, since we are looking at ultraviolet wavelengths, the main problem is any kind of contamination, especially organic contamination and particulate contamination, will lead to serious consequences. And this is really, really tough in the sense that the level of cleanliness we need to maintain in the labs while we are, material touching any kind of material, at the level from the material selection to the material coming into the lab to handling it, people who are handling it, all of them have to be trained in this clean room procedures. And to do that and make sure that is followed strictly is a big challenge. So such hyperclean labs do not exist in the country. Not many exist in the country. So we had to build one to start with. So before suit was built, we had to first build the lab. When we didn't have space in IUCAA in Pune to build the lab, so the lab was built in ISRO. So kindly provided us the big hall. So first of all, we had to go there and build the clean rooms and an integration facility, and then train the people, set up the protocols to get going. In addition to particulate contamination, we have also problems with organic contamination. Even the grease on your fingertips, you sneeze, it's a problem. So all the time we are working under COVID protocol. All the labs, we are double suited like space, environment, and that creates a lot of problem. You might think this is trivial, but it's a big problem. For example, someone who is going into the lab with this equipment and working there for hours, oxygen becomes a problem in the room. They want to take a bio break, it's a problem. Any bio break is an hour of break. You can't just walk out and come back in. It's an hour of break in the whole process. So, and to make people follow that for year and a half, 2 years strictly is a big problem. And that is connected with the HR problem, which I talked about earlier. Once people get trained to these things and we don't retain them, it's a big loss. Another big challenge, as I said, is scattering. You are looking at the sun, and you want to get very high photometric accuracy. Any tiny level of scattering is a problem. So we want to make mirrors of the instrument, which is really polished. The LEOS, which is one of the ISRO's facility, they made these mirrors, but they were struggling to get these specifications. They are really challenging. They're pushing them to the limits. And also careful design of the optical enclosure. The entire instrument inside has to be carefully designed to make sure the scattering is minimized to sub-percent level because you don't want any level of scattering contaminating your instrument. Thermal stability is another important consideration. We want the instrument to be extremely stable. Plus minus 1 degree on ground do not look challenging. It's trivially exceed. But when you have to achieve that kind of stability on an instrument which is out there in the space, it becomes a big challenge. And this was again pushing the ISRO people to get this thermal stability achieved and demonstrated to be a challenge. Of course, the detector has to be cooled. The other challenge is a big challenge is you can see this is polar spectrum, and that's the part which we are looking at. And that's about 200 nanometer wavelength, and that's about 400 nanometer wavelength. The solar spectrum increases huge factor. factor of 20 or so, even within your band. So that's a large factor. And on top of it, you have filters which are less than 1 nanometer wide in filter bandwidth at the low wavelength end, and more than 40 nanometer wide at the broad wavelength end, long wavelength end. So not only the solar spectrum is increasing, you also have this wide range of filter bandwidth variation between narrowband and broadband. Multiplied that with the fact that when the flares happen on the sun's brightness can go up by a factor of 10 or even more. So on the one end, you have to look at the quiet sun in a narrowband filter at the short wavelength end where there is barely any signal. And at the other end, you have to look at the broadband filter sun when it is active and with a very generous level of wavelength coverage. And that puts a lot of challenge in the dynamic range which you want to achieve with the instrument. And this has to be, auto adjusting. You cannot set an exposure and say you observe. You either saturate or too little light. It has to be sensing what the sun is doing and reacting to it. And you can't control it from ground because it's, as you know, it's an L1 point. L1 is visible to you only when the sun is up there. It's in the direction of the sun. And so sun sets, the satellite is not visible. So the satellite has to have onboard intelligence to manage this onboard and react to situations on the sun as required. So that's a big challenge. The other challenge is sun is very hot. So all the radiation from the sun enters the payload is going to heat up everything and create havoc inside, scattering, heat load, etc. So of the total radiation which is coming in the sun, we want only 10 to the minus 3 or 0.1% or maximum 1% of the light to enter your payload. The rest has to be rejected. If they enter the payload, it's a big problem for you. So that's another challenge. So you have to have a mechanism by which 99.9% of the light in the in-band is rejected, and even more of the out-of-band light. Because sun is brighter, as it goes to longer wavelength, it gets brighter. So out-of-band radiation has to be rejected even at the longer wavelength. Otherwise, they will come and ruin your images. So they have to be rejected even further. So that is a big challenge to achieve that. Almost all the light of the sun is rejected while the radiation itself is changing by an order of magnitude or more across the band, and how to balance it so that you get a flat curve at the end of the day across the band. That's a big challenge while rejecting the outer band. And that requires some planning and designing things. So I'll not go into the details of it. The other challenge is, since the satellite is at L1, 1.5 million kilometers away, the link to the satellite is very slow. In today's parlance, it's almost 0, 8 Mbps kind of link. So if you are producing a lot of data on the sun, for example, if you look at the whole sun, round the clock in these 11 filters, 24 hours is going to create 135 gigabytes of data. But the downloadable limit is 21 gigabytes across all the instruments, including VHC, this, that, everything. So that's a huge volume. I mean, you can't generate that data, but because it can't be sent back to Earth within the given time. So that's a big limitation. So what you will need to do is to, of course, observe the sun in full frame to see what is going on. And when action is happening on the sun, you have to, of course, we'll use compression. That is one thing, but that's only a factor of 2 gain. That's nowhere near what you need. But on top of it, you also need to switch from full disk to region of interest observation. So some region of the sun becomes active. It has to automatically know, satellite has to automatically know this region is going to become active, put a box around it, and only take data from there. You can't take the full disk because you can't send it back anyway. So that's a challenge. That intelligence has to be built on board. Anyway, so that leads to a pretty complex operational mode requirement of the sun. In addition to that, in order to know where activities are happening, you need to taking full disk images. If the full disk images are not there, you don't know what is going on. So that has to be filled in. Then the other thing is, when this action happens, you see this hard X-ray light curve for a flare, which precedes a tiny amount of time with this UV emission. As I explained, the hard X-rays happen when the magnetic reconnection happens at the top, and when that plasma drops through the tubes and hits the photosphere, the UV emission happens with the photosphere heats up. That's a little bit later. So what we want to do is to catch, using the hard X-ray instrument, which is Helios on Aditya-L1, and if the moment it sees an indication of a flare coming up, let it send a trigger to suit, so that suit switches into a flare mode, so that it observes the flare. In the flare mode, puts a box, try to detect the flare is happening, put a box around it, and take rapid images around that flare region. And this has to happen autonomously. And that's another challenge. Anyway, that's a flow chart which says how we get triggers from both soft X-ray instrument and Helios, as well as the self-triggering. There is a self-triggering mode you continuously take. It varies. It can be a minute. It can be a few minutes. But it varies. It's not and not every time we may get it's in the right order also. In the simplistic picture, this all looks good, but sun is more complex than that simplistic picture I was trying to draw. And that's what we are trying to understand. So in the good times, it's about tens of seconds to a minute. And so flare localization and detection has to happen, and then all that has to be built into the filter to the instrument. And of course, as I said earlier, because the flare happens, the dynamic range has to be adjusted, the exposure time has to be auto-adjusted, and so on and so forth. Okay, and then sun rotates. So if I put a box around the sun and the active regions move, the box has to track the active region. And that active region motion is also relatively well understood. It's not the same rate. It changes as a function of latitude. So as a function of where your active region is and how it moves, you have to have that box track the activity on the sun. And you have to build in intelligence on board to do that. Of course, the way the sun appears on your CCD could be tilted. You have to correct for it and so on and so forth. Anyway, this is just a list of the various modes which you come up for different kind of studies of prominence flares, full disk, radiant studies, full disk suns and climate campaign, etc., and what kind of modes have to be built into on the satellite to deal with this kind of studies. So this I mentioned already. This is just a summary. You have a flare detection mode with Helios and Solex, the soft X-ray and hard X-ray, and self-triggering, region of interest tracking, adaptive exposure control, mode switching, etc., etc. So what we ended up doing, because of all this complex requirement, was to actually build in an operating system on board, which lives on it's like a small kind of operating system which lives on the satellite. You can send commands to it and program it to behave in various ways. Because these are the modes which we can think of today. It's a 5-year mission. It might last for even 10 years. Every possible science observing mode is not thought of today. I think people have imaginative, creative. They will think of new things tomorrow. So the satellite has to be able to adapt and to be able to deal with those kind of demands. So we had to end up making it really flexible by building an operating system and making it do what you want to do by sending a set of programs. So you upload a set of programs which executes, and if you want to change the programs, you can upload a new set of programs so that it does what you want. So that was a big challenge. Anyway, so all that was behind us on this fantastic day in September. when September 6th, when the mission was launched from Sriharikota. Picture perfect textbook launch. And it is going to this location, 1.5 million kilometers. Of course, it did a lot of going around the Earth, raising Earth's maneuvers a few times, and then it exited Earth's sphere of influence and went about 3 months it took to get to L1, traveled at 1.5 million kilometers, and then it got injected into a big orbit. It's about 4 lakh kilometers size, and about 180 days to go around once into that orbit. Again, all worked perfectly. So that's just a slide of timeline to show you, in spite of all these challenges, it was pretty quick. We received the money from ISRO in December 2016. And we were launching in 2023, September. So in spite of having to build the lab itself and training human resources and so on, I think it's a did a pretty good job doing that. But we don't want to repeat that if possible. We need to retain the people and the know-how for the next mission. Anyway, suit was powered en route to L1 on 20th November. And the suit door was also opened en route on 6th December. And then the same day, we got the first images from suit. That is a movie which shows the door opening. There's a camera which is outside the satellite, which looks toward the door. And that's the time when the suit door was opened and exercised a few times, opened and closed, which is the most important day, and that is first light on December. The first light images, we are ready with all the software required to look at the data, download it, analyze it, produce these beautiful maps. And those, we are showing the 8 narrowband filters here. Of course, there are 3 broadband images also. Sorry?
So the resolution is very different from the different bands. It's just that at some bands there's no structure. The broadbands it's whiter.
Yeah, so that's an interesting observation. So these are the magnesium bands and calcium. They show a lot of structure because there's a lot of activity there. And some of the other ones which are more photospheric don't show much activity. Now, but that's the current know-how. Now, what we are seeing, and now this is the first paper going to come out, we are seeing activities at those wavelengths which theory predicts you shouldn't be seeing anything. So we are already seeing something very interesting. You don't understand it, but there are some speculations of how this could work. But as I said, this was the expectation. Our first images were kind of textbook images. They didn't see anything. But when we started observing some of these off-limb features, and we are seeing now features which at other wavelengths which should not be seen at the photospheric heights and so on. That's okay. So then after L1 insertion, we were continuing with the performance verification, which ended by the end of June. We are in the guaranteed phase time now, which lasts about 9 months from now. And then suit will be available for proposal submissions after the guaranteed phase. So anybody in the country can submit proposals. It will go to a usual time allocation process. And if time is allocated, you can get your data. We'll be getting to that phase pretty soon. And we plan to have 5 years of nominal operations, but maybe almost nothing on board which can expire except some fuel which is required to maintain the orbit. But the ISRO is telling us that will last more than 5 years. So we'll see. So these are some of the, again, first light images. You see this big disk as well as a zoomed in region, and then the zoomed in region as in different wavelengths on January 24. And that's an active region, and you can see these active regions firing up and how different they look in different filters. Of course, you see common structures. These two structures are common across, but you see detailed structures at different wavelengths, and they become turned on and off at different times, and so on and so forth. So all that science is in that. Sorry? Yes.
I don't understand how much data are you collecting and how are you compressing that?
Yeah, so we do compression, but that gains the factor of 2 kind of thing. So all the complex operating modes, which I showed in one of the slides, but did not delve into the details of it, are designed in such a way that we collect enough data which can be transmitted within the next 8 hours.
So basically,
There is a limit.
You with much less data than you gathered. You focus only on one particular.
So that's what I was trying to show here. So this is a full disk image, of course, but we know as soon as we know this region is going to do something interesting, you put a box around it, like this, the yellow box, and then take data from that region. And these are the images which you get from that box, which are shown here. But now we are doing it much faster. If we are taking full disk images, there is a certain rate at which you can take images. But if you are taking a small box, you are taking faster. So it's not a linear thing. In the sense that full disk image, one image, large volume of data, but taken slowly. Small areas, small amount of data per image, but taken much faster. There's a play between these two, which you have to define in a way that within 24 hours, irrespective of all the autonomous activity that happens out there, you collect only enough data which you can download in the next 8 hours with the available bandwidth. There's a little bit of playing around happens around on board for that.
Roughly the same time, then you will be able to
Multiple active regions. So there is also a science-driven prioritization process. I did not even delve to that. So for example, this flares on the sun could be of various classes, and some are very rare compared to the other. So you would want to collect the rare one. So if a rare phenomena happens while we are observing a less rare one, but more frequent one, you will switch to the rare one, because that's one we. So there are some onboard algorithms to play around that. Sorry? How or what? Automated, yeah. Onboard, because you can't control the satellite most of the time. 16 hours a day, you don't see it. It has to be on board. And you might think in modern computers with a laptop like this, or probably your mobile phone, you can do all this with the computing power of your mobile phone. You can do all this, but you want to flow it up there. The kind of chips you can fly are produced probably 30 years ago. So there is and they have to be space qualified, and this environment is not protected by the Earth's magnetic field and ionization, material free. It's out there exposed to everything which comes out of the sun. So it has to be space qualified to a much higher level than the normal thing, which means there are fewer number of electronics capability you can build it up there. So within those limitations, to build these capabilities is the challenge. Otherwise, all that I was talking about, you might wonder as a BTech student or something, okay, I can do that my Raspberry Pi chip. Right? You can do that, but the challenge is when you have to space qualify. Right?
what are the purposes that building on that activity? Why? And it is that also get at what purpose on the
Sorry, what the
why there there is one activity, but the active, when the query is that, certain threshold has crossed. On what threshold you have defined for the output activity?
Yeah, there are multiple ways. One is the trigger coming from the high energy X-ray instrument. That is expected to see a flare initiation seconds, tens of seconds ahead of it appears in UV. So if a trigger comes from Helios, we will immediately switch into a mode where we'll rapidly take full disk images and see what region is. I mean, there's a complex process where you not only want to see how it is increasing, but the rate of increase, and the rate of increase is consistent over time, et cetera, et cetera. So there's not just a simple threshold, it's also rate. So rate of change and how the rate of change changes as a function of time in order to avoid false triggers. Otherwise, there's a lot of false triggers comes. Sun is so active, so it triggers a lot of false triggers. So there's a way in which things are expected to change. You tune your thing to pick those ones. Sorry, what is that? So that's what I'm saying. So Helios trigger, and then we also get trigger from soft X-ray in case soft X-ray sees something in advance to us. In addition to that, in the operational modes, we are taking full disk images of the sun every minute. And then we accumulate a running set of 4 images like that, and then apply our filters on those 4 images over the entire region of the sun and see if something interesting is going on in any region. If anything is interesting according to our definition of interesting, which can be changed later, but currently we have a definition of what is interesting. If that region satisfies that, then you put a box around that region, and well, so it's a built-in mechanism to do that. Okay, so this is just a time plot just to show that our data pipeline is ready and running and so on. This is a double flare on a particular day, 22nd February. There were 3 flares actually on that day from a particular active region. The first one was not caught by us, but the second and third, this is the first one, this is the second one, and this is the third one, which was caught. Of course, this is the light curve, for example, from multiple other instruments, GOES, AIA, etc., compared with the suit, so multiple filters on suit. So we see that we get this data, we can follow the light curves, we can track them, what's going on. In addition to what is going on full disk, we also can look at the sun off limb because we have a much wider field of view. And this is a fantastic event which happened as an eruption from an active region. You can see the particle going away and it accelerates. And this screen is not visible. All the features are not visible. And this loop, I don't know if you can see here. And that's an interesting thing which is predicted by theory, but not have been observed in real life previously. So we are for the first time seeing that happening, that post-flare loop where the particles drop from the bottom and so on and so forth. So these are just the first images. Similarly, another ejection which is happening, which happened on 27th May. You can see that object becomes suddenly active and the post-flare activities. So, so that's a overall status of the instrument, where it is. The science of suit is managed by what is called the Suit Science Management Panel, which has a lot of members across the country, and one from Max Planck Institute in Germany, but remaining people from across the country. And they lead I will skip this slide. The Science Management Panel is overall management of the science, but they lead the different science activities of suit. These are the key science programs which have been identified for suit and who will lead them among the science management teams. So they have all been identified. So they are getting data at the guaranteed phase. They are the investigators of soot. They are getting this data right now, and they are looking at their own observing proposals and plans and so on and so forth. So that's all active right now in the guaranteed phase. Once the guaranteed phase is over, a few months from now, it becomes open for public to apply for time and use as they wish. So that's a last slide. I'll stop here. This is just a collage showing various stages of soot, and but which I want to point out is that's the way in which you have to keep working in the lab. Every activity related to soot has to be done fully suited up with double clean clothes, and so on, and becomes a challenge in itself. Thank you very much. If you want to know more about soot and what is going on, please follow us on this website.
I will open for questions.
Just a question about onboard intelligence. So you need three factors there. First is the precise design of the detection, and then precise localization and exposure control. So how much is the real time you can do that currently with that, and what is the repeatability of that?
How much is the time between receiving a trigger, for example, from
So you
Helios?
have to localize, you have to see the...
So receiving a trigger from Helios will not even a trigger. Helios is just going to send us raw data. Just X-ray flux as a function of time. The time series data. So we have to use that data to generate a trigger ourselves on board. So that we need to understand a bit of how Helios is behaving to put our... so there's a complex algorithm there. And then once the Helios says something is going on in the sun, but we don't know where it is, so you have to localize it. And then when you localize it, you have to make sure it's sustaining, because otherwise there'll be a lot of random, X-ray data is very noisy, right? You can lead to a lot of random triggers. So at the moment, all this can be done in less than a minute. The satellite can react from Helios trigger reception to flare localization, and switching into a flare mode will happen in tens of seconds at the moment. There's a little bit of uncertainty there, because to some extent it depends on what soot is doing at that exact point of time. Sometimes the onboard algorithm is such that you say, I'm taking a data right now which is of high priority, please don't interrupt this one. Let this finish and then switch. So if that kind of situation is there might be a little extra time, but if soot is ready, it is less than a minute. It's like more like 20, 30 seconds. But if it is internal trigger generation, you can be late by 4 minutes even, because you take only one image at a time. So you get one at the last of the previous cycle, and then you have to take at least 3 more to get to the trigger mode. So it might be up to 4 minutes. So that's a range.
Quick question about this narrowband filters. So these are simultaneous, you have filters, or you are one by
one after the other?
One.
Filters, there's an algorithm which picks the filter depending on the particular observing mode. So which is the region of interest mode and the flare mode of active region tracking mode. Every few seconds, a new filter image comes. But if it's a full frame mode, depending on which high resolution or low resolution, it can be 10 seconds or 15 seconds.
These observations, all the instruments can simultaneously observe the sun and also at the same region of interest, or there is flexibility? So when one instrument is making observations, do the other instruments have to switch off? Or
You mean VLC and Helio? No, they are all looking at the sun all the time.
But always at the same region.
They are all hot. No. So we in soot has these different operating modes.
I see.
Coronagraph has its own modes. So that is controlled by IAA.
Yeah. Okay.
Then Solex, what it does, or Helios, what it does is controlled by their PU. So we have a payload operation center in IUCAA, through which the next day's activity is uploaded, and then suit autonomously does that. Similarly, VLC will upload their thing from their payload operation center. Of course, the teams, if you notice, have members across the payloads. So Nagaraju is part of VLC, Durgesh. I mean, so people do talk and try to optimize these. For example, if there is a science case where the coronagraph data is and suit data combining is useful, you create a campaign like that. You plan things like that. But in general, they are independent.
Yeah. Okay.
Thanks for a very interesting talk, first of all. I have a very speculative question. You showed this butterfly diagram of the solar active regions. Is there any evidence for about 100-year periodicity in that diagram? Or
yeah, the data showed over 100 years. Right? Or you mean periodicity at 100 years? Why do you expect 100 years?
No, so just from looking at the
Are you saying is there a longer harmonic embedded in the 11 year?
Exactly.
I don't know.
Okay.
I don't know if people have looked at it. I'm sure people have looked at it because sun is something which has been observed for 200 years now, right? And sunspots are the most interesting things people have been charting and so on. So if not as reliable data as we have for the past 100 years, some data is available. So if not over a cycle of 100 years, at least there is enough data to look for whether there's 20-year cycle or 30-year cycle or something. I mean, I'm sure people have looked at it, but I don't know the details.
Okay. And one more thing, you showed a video of this huge coronal mass ejection. I was wondering if that's an observation or a simulation or just an animation.
Is it a?
Is it a real observation or is it a
data?
No, so there was a video of a coronal mass ejection at, I think.
The first one which I showed.
Yes.
That.
Yes, that was an actual data.
The one which I showed toward the end was data.
The earlier one.
In the section of context development, somewhere real data, somewhere simulations. So it was a mix.
I was just wondering.
The granules you're showing and the activity of the sunspot, those were real data. I think the ejection itself was probably a simulation. I'm not sure. Maybe it's a simulation.
So I was just wondering about the time scale. So even in the final animations here, I think my question is relevant to that as well. Is the real time same as the video time, or is it scaled up or scaled down?
The one which I showed
at the end.
The typical timescales of this activity, the real activities of the order of, I showed that plot, right? It's of the order of 10 minutes when the real activity happens. So that timescale may be 20 minutes, an hour. So our standard mode is, if you go to a flare mode, it sits and observes the sun in flare mode for 2 hours, which we think is the max some activity will continue. By then, all interesting things would have happened. So tens of minutes, I would say. But the real thing which we want to see is the flare initiation. That happens at the very beginning, which is of the order of few minutes. Once the initiation has happened, then the curve has been observed. And
so that's more interesting.
So early phase is what nobody knows what is going on. That's what we real value addition from suit.
Thanks.
Yeah, is it okay? So, sir, we have this area of interest through which we basically narrow down the area we're interested in, right? So that process is iterative, is it? Like, so let's say we get a trigger from Helios. There's a massive flux change, and we immediately start the suit, and we start tracking. We don't know the spatial location, basically.
That's what Devendra was asking.
Okay.
So the moment Helios tells you that something interesting is going on the sun,
yes,
we don't know where it is.
Yes.
So suit will do activities to localize it, because it has been taking this image every 1 minute.
Right.
You'll go back to the historical images and see where the activity is happening.
Okay.
And whether that activity is consistent with a flare-like behavior, and then we will put a box around.
Okay, okay.
So we already are collecting continuous data.
Right. Okay, okay.
Historic data is available on board.
Two questions. So first one, you mentioned 8 hours downlink time, right? Is that when India is in the
But the
sun
sun is
direction?
visible.
So because the science, a lot of science can be done if there is more data. Is it hard to have agreements with other countries to downlink this data?
Yeah, so I'll send you Dr. Somnath's email address. Why don't you send him an email? No, we have been trying to convince ISRO
Okay.
that we do need more ground stations and more capabilities to download data, but it costs money, which is hard to come, right? So this is a typical situation where you're penny wise and pound foolish, where you spend a lot of money sending a mission like this. And then at least for a year or 2 years, if you have that arrangement where you can make full use of the potential. And you can imagine if it's round the clock visible, we can generate real-time predictions. But right now, I collect data for 24 hours. I have to wait the next morning, 8 hours before it comes, look at it and say, hey, something interesting is going on the sun, and this might come and blast Earth. By that time, it would have reached us and blasted already. I know only next day. But I can predict it on board. But that information, there's no way to transmit because we don't have around the time. But we have been telling this and pushing for this, but it's not happening.
So my
It's
second
a real limitation. Yeah.
Okay. My second question was, so the images that you showed, so currently are those diffraction limited or the mirror figure limited or pixel sampling limited?
Yeah. So the primary mirror has been designed to deliver diffraction limited images so that it does not become the bottleneck in the image quality. But as you can see, there are a lot of elements in the optical train finally, and it's a wide field. So all across the field, it's not diffraction limited.
Okay.
So our aim was to have 1.2 arc-second resolution on the sun, finally delivered image quality. And we are getting about 1.8 to 2. So we are not got to 1.2. It's slightly worse than what we designed it.
So it's not primary, but something else.
Something else in the optical alignment. Mainly the thermal filter in the front,
Nice.
which gets heated up because it's getting the total blast to the sun, although it's reflecting most of it off, it's heating. While it is a window, its shape is changing because of the heating. And that's introducing some aberrations. So we knew it is going to happen. And we had methods to solve it, but we always in the mission kind of time, you don't have all the luxury to say, give me another 6 months, I'll fix this problem, and then we'll plan the launch. So the launch is ready, you have to go. So we could have resolved it, but then we said, okay, given on the balance, we'll go ahead with 2 arc-seconds. We'll leave it 2 arc-seconds.
Thank you.
Per day. Why it cannot be more?
Because it's so far, and how big a dish ISRO has, they have a 32 meter diameter deep sky network antenna in Bangalore. So when the sun is visible over Bangalore, you can download data at the fastest speed that dish can handle.
And compared to Mars orbital mission, what is download rate there?
That's much smaller. Nothing. Mars is spending very little data back. This is continuous imaging data. Chandrayaan also is not producing that level of data. The data rate here is much higher than, data we can technically produce is much larger than any of the other missions.
And
so they're much coarser resolution. The detector sizes are much smaller. This is a 4K by 4K image at higher angular resolution. So it produces a lot of data per image.
Yeah, changing data transfer mode, can we improve the download rate? Or
this is the best ISRO has now. Now, as Joe was asking, at the moment, the only other option is to collaborate with European Space Agency or the Americans or someone else, so that you get ground station link from their facilities. So you can get round-the-clock ground station links, but they charge money for that.
One hypothetical extension to that. Suppose you make a data center at satellite, polar satellite, you download huge amount data there and later transfer to
Yeah,
ground.
that's another
Is it
mission.
possible?
Yeah. I mean, much cheaper than that is to get data downlink time with one of the other collaborators. I mean, other space agencies. Japan, Europe, US. So we can get downlink time from all of them. And typically, ISRO will have arrangements where you say, okay, you get downlink time for this facility of mine. I will give you downlink time for that facility of. You can arrange some exchange programs, etc. Very often that is done. But at least so far in this mission, it has not happened.
Thank you.
Maybe they are waiting us to demonstrate that it works and the data is really good. And then if there is enough demand, maybe it will happen. It's not that we cannot start now. Next year, when there is enough observing proposals from the community, they might say, oh yeah, really, let's get some more downlink time. It's an ISRO decision. It's not? No, that's not the restriction. No, it is a restriction that is for a given antenna, there is a fixed bandwidth. But if you increase the time over which you can get it, 24/7, you can get more data and also more real-time data. As soon as a flare is happening, you can, or going to happen, you can say, hey, something is happening, spend this word around across the community and people can react. They can turn all their antennas there and look. So that's not happening right.
There is a question on Zoom room. Professor Datar, if you can hear us, can unmute yourself.
Yeah. Can you hear yourself? Can you hear me?
Yes.
Yeah. Okay. My question relates to this. Are there any particle detectors in the sense of, let's say, protons, alphas, or even neutrons, perhaps?
Yes. Out of the payloads on the sun, DLC, Soot, Solex, and Helios are the remote sensing, so-called remote sensing. They detect photons from sun. But then there are PAPA, aspects, and magnetometer. Those three instruments are measuring particles from the sun at L1 and the magnetic field orientation and changes in magnetic field at L1.
Okay.
So there are in situ measurements at L1 by these particle, and these particle instruments do cover a wide range of particle masses, both charged and uncharged.
And what is the energy range that they measure?
Energy range of the particle detectors?
Yes.
I'm not sure. I think I have a slide on that. Let me see if I can pop it up. What was projected, I can say here, but what was finally achieved, I don't know. That is still being analyzed. That data is still being analyzed. So let me see if I can find out that graph. The energy range is a wide range, all the way from alpha particles to heavy ions like carbon and so on, oxygen and so on. So the whole range is probed. Let me see what those corresponding energy ranges are in one of the slides. Yeah. Can you see the slide?
Yeah, I saw something like 0.1 keV to 20 keV, and then another one.
So there are multiple packages going from 0.1 keV to 5 MeV.
That's right. Okay.
And 0.01 to 25 keV. So there's an overlap between those two. And then there is a magnetometer.
Okay.
So I'm not sure which range correspond to which specific species, etc. But as you can see, it's a wide range.
Yeah.
And I'm not sure the entire range is delivered in the final version, this is at some phase
Okay,
not planned, but I'm not sure the entire range is delivered finally.
okay. So this would be there on your website, right? The aspects experiment.
Sorry?
No. The information about what aspects is doing would be there on the
Aspect
website.
website. And this aspects and Papa, those instruments are standard instruments. I mean, they are not, they are not driven by proposals. They are just sitting there and measuring whatever is coming their way.
Okay.
And that data is available.
Mhm.
Yeah.
Okay. Thank you.
Our Satya had written down the message. She's asking for what kind of FPGA or ASIC you have used for your onboard computation.
Yeah.
Because you
There's
mentioned
some
limitations.
silings, but not silings. Silings don't fly on board. I can tell you, I have forgotten. It's
1280.
quite a while ago.
1280 or something.
There are 3 FPGAs on board. One is all from the same family,
The
but
qualified
different
part list of ISRO, what they allow for this.
yeah, different capabilities, but they are
Hardened
qualified.
electronics, yes.
But I don't remember the exact model number at the moment.
Yeah.
But they are all something like 25 years old.
Yeah.
So none of the current generation FPGAs. Even the analog to digital converters, which we use for data conversion, etc., are all
Correct. Qualified part list of ISRO is not.
Yeah, you have to use
30
them.
years,
I mean,
so,
otherwise, you have to go through a space qualification process, which will prolong the mission time.
Okay, I think that's enough time we have for questions. And thanks once again for a wonderful lectures and question answer session
for
for
all
Professor Ram. I request everybody to join for interactions during the tea. So, questions. Thank you very much, everyone.
Thanks.
Sorry.
I have 3 questions. Hello?
Yeah, please go ahead.
I have 3 questions I put in the chat.
Yeah, fine. We'll try to answer you later on. Thank you. Yeah. We will answer you later.
You can, the chat will vanish pretty soon, so maybe you can forward it to me or something.
You are going away. When you will answer?
Oh, you want the answer now? Okay.
If you are not interested, it is okay. Fine for me.
Okay, thank you.
We are run out of time, sorry, but you can always type it on or send in an email and we'll get back to you on the answers.
No, I already typed it in the chat.
Fine, we'll save it and I'll get back to you. If it is there in a chat, we'll save it. Thank you.
I'm sorry. It's okay.
Yeah, I understood. Quickly become something. That was